As we discussed previously, light rays can reflect off the surface of spherical mirrors to form an image. The properties of the images that are produced depend on the type of mirror and the distance the object is located away from the mirror. We can use a graphical technique known as ray tracing, which is the hallmark of geometrical optics, to determine the location, orientation, and size of the images we see. We will utilize some specific paraxial rays and apply the law of reflection at the mirror surface. We take advantage of the fact that paraxial rays leave a point on an object and intersect or appear to intersect at the corresponding point on the image after reflection. This technique also demonstrates what's known as the principle of reversibility, which states that if the direction of a light ray is reversed, the light ray retraces its original path. Let's begin with the concave spherical mirror. Three specific paraxial rays are especially convenient to use in the ray tracing method. The rays are labeled 1, 2, and 3, and when tracing their paths, we use the following reasoning strategy. Ray 1 is initially parallel to the principal axis and therefore passes through the focal point F after reflection from the mirror. We will see that there is always a corresponding relationship between parallel rays and the focal point. Ray 2 initially passes through the focal point F and then is reflected parallel to the principal axis. Ray 2 is analogous to Ray 1 except that the reflected rather than the incident ray is parallel to the principal axis. Finally, Ray 3 travels along a line that passes through the center of curvature C and thus follows a radius of the spherical mirror. As a result, the ray strikes the mirror perpendicularly and reflects straight back out along the same line. For the concave spherical mirror, there are three different cases to consider based on the location of the object. Let's take them one at a time. For case 1, we consider the object when it is located beyond the center of curvature C, as the figure shows. We represent the object with an upright arrow whose tail is in contact with the principal axis of the mirror. Let's now consider three paraxial rays we mentioned earlier. For ray 1, we consider the parallel ray coming from the top of the object. Upon reflection, it passes through the focal point. Ray 2 comes from the top of the object, first passes through the focal point, and then after reflection comes out parallel to the principal axis. We see that the two reflected rays intersect, and this determines the location of the top of the image. In principle, only two rays are required to determine the location of the image, but let's add in the third ray as well. Ray 3 comes from the top of the object and passes through the center of curvature. Upon reflection, it travels straight back out along the same path. Notice that all reflected rays intersect at a common point and show the location of the top of the image. Since the intersection of the reflected rays forms below the principal axis, the image in this case is upside down or inverted with respect to the object. Notice also that the length of the image arrow is shorter than the length of the object arrow, which means the image relative to the object is smaller or reduced. And finally, since the image is formed by the intersection of the reflected rays, the image is a real image. We didn't have to do any extrapolation of reflected rays back behind the mirror. To summarize case 1, in which the object is located beyond the center of curvature, we find that the image is real, inverted, and reduced. Now consider case 2, where we move the object closer to the mirror, so that it is located between the center of curvature and the focal point. We again consider three paraxial rays to determine the location and properties of the image. First, we consider ray 1, which is a parallel ray coming from the top of the object, and upon reflection passes through the focal point. Ray 2 comes from the top of the object, first passes through the focal point, and then upon reflection comes back parallel to the principal axis. Notice that rays 1 and 2 intersect to show the location of the top of the image. We also consider ray 3, which comes from the top of the object along a direction as if it came from the center of curvature C. It then, upon reflection, travels straight back out along the same path. Notice that all three reflected rays intersect at a common point to show the location of the top of the image. Again, the top of the image is located below the principal axis, so that, as in the previous case, the image is inverted with respect to the object. However, the length of the image arrow is now longer than the length of the object arrow, so the image in this case is enlarged. And since the image is formed by the actual intersection of the reflected rays, the image is again real. To summarize case 2, in which the object is located between the center of curvature and the focal point, we find the image is real, inverted, and enlarged. For case 3, we continue to move the object closer to the mirror, so that it is now located inside of the focal length f. We again consider three paraxial rays to determine the location and properties of the image. For ray 1, we consider a parallel ray coming from the top of the object that upon reflection passes through the focal point. For ray 2, we consider a ray that comes from the top of the object, along a line as if it came from the focal point. Upon reflection, the ray comes out parallel to the principal axis. Notice that the reflected rays 1 and 2 do not intersect, as they did in the two previous cases. Finally, we consider ray 3, which comes from the object, directed along a line as if it came from the center of curvature. Upon reflection, it travels straight back out along the same path. Now we can see that all three reflected rays do not intersect, but rather diverge after reflection. However, if we now extrapolate the reflected rays back behind the mirror, we see that they appear to emerge from a common point. This locates the top of the image. Since this intersection is above the principal axis, the image will be upright with respect to the object. Also note that the length of the image vector is larger than the length of the object vector. Therefore, in this case, the image is enlarged. And since the reflected rays diverge, and we have to extrapolate them back behind the mirror to find the location of the image is virtual. To summarize case 3, in which the object is located inside the focal length of the mirror, the image is virtual, upright, and enlarged. A makeup or shaving mirror functions exactly in this way, as the figure shows an enlarged and upright image is produced. Next, let's consider images formed by a convex spherical mirror. This is simpler than the concave mirror, since we only have one case to consider. As we will see, a convex mirror always forms a virtual image, regardless of where the object is located in front of the mirror. However, the three paraxial rays we consider here are slightly different than those for the concave case, since the focal point and center of curvature are now located behind the mirror. The first ray is a parallel ray that comes from the object. Upon reflection, it gets reflected away from the principal axis, as if it appeared to come from the focal point behind the mirror. We use a dashed line to extrapolate the reflected ray back behind the mirror to show that this is indeed the case. The second ray we consider is a ray that comes from the top of the object and travels along a line that is directed toward the focal point behind the mirror. In fact, if the mirror weren't there, this ray would pass right through the focal point. However, the mirror gets in the way, and this ray comes out parallel to the principal axis upon reflection. Since the first reflected ray and this one diverge, we extrapolate the reflected ray back behind the mirror. Notice that it intersects the first extrapolated ray. This locates the top of the image. We also consider a third paraxial ray, which comes from the top of the object and travels along a line toward the center of curvature behind the mirror. Again, the mirror gets in the way, and this time the reflected ray travels straight back out along the original path. We extrapolate this reflected ray back behind the mirror and show that it intersects the other two extrapolated rays. Since the intersection of these rays is above the principal axis, the image is upright with respect to the object. The length of the image arrow is less than the length of the object arrow, so that the image is reduced. And since we had to extrapolate the reflected rays back behind the mirror to find the location of the image, this image is virtual. To summarize the image properties of a convex spherical mirror, we only have one case to consider, and we find that the image is virtual, upright, and reduced. There are many common applications for convex spherical mirrors. They are used in stores to monitor patrons, and also as mirrors on the passenger side of automobiles. In both cases, the application takes advantage of a wider field of view compared to that of other mirrors.